Hi guys, so we are back with the section on DC machine dynamics. So in this section we are looking at basically transfer functions to model the way a DC machine will behave uh, in terms of the changes in different parameters in the machine. And we will basically derive the transfer function of the motor to represent the dynamics of the machine. So you will find that we will convert our equations from time domain to your S domain, and we'll apply Laplace transform, and that will enable us to show the transfer function, and also enable us to look at whether the response that you're getting following a certain change in, for example, the torque, will basically affect the speed of the motor. And so we will derive the transfer function and look at, for example, your damping ratio and the natural undamped frequency of the system. All that we can basically represent in the S domain. So before we derive the equations, there are a few assumptions that are made in the derivation of the transfer function for the DC machine dynamics equation. So the first assumption is we assuming that the brushes are narrow and there is a linear commutation, right? And the second one is the armature MMF is assumed to have no effect on the total direct axis of the system. Just give me 1 second, please. I'm muting now and just answering one urgent call. Okay, guys, I'm back. Yeah, so as I said, we were taking those through few assumptions. The last assumption, what is also very important in the derivation, is that we neglecting the effect of saturation in the machine. Right, so if we go back to the basic DC machine, the torque on so that's your electrical torque output of the machine, depends on those parameters. So that's your armature current, and that's IA, and the flux in the machine, right? So that's the phi D, it's the total direct axis flux, and Ka is a constant that is basically shown in equation 3, right? So it's PZA over 2 pi times A, where that P is the number of poles, ZA is the total number of conductors in the armature winding, and A is the number of parallel paths through the armature winding. So this is a constant, right? And the armature, so that's your induced voltage in the machine. And so that's basically given by also the product of the speed of the motor times the flux and constant Ka, right? So when we use that assumption here, which is we're neglecting the effect of saturation, it means that the flux in the machine is now proportional to the field current, right? So your field current and the flux will basically be proportional. So we can rewrite those two equations, right? So as you can see here, the electrical torque and the induced voltage in the machine, I've written it instead. We've replaced the product of the constant Ka times phi with Kf times If, where If is now the field current in the machine, right? So we can see that the electrical torque and the induced voltage is basically represented in terms of the field current, and this is the armature current, and here we have the field current and the speed of the motor. Okay, and now Kf will basically become a constant, which we will basically explain it in more detail when we go through the examples in the tutorial. Right. So now the voltage of your field circuit. So now remember, your field circuit has an inductor and obviously the coil will have certain resistance. So you'll have two parameters when you write the equation. You'll have the parameter that's representing the drop due to the resistance of the coil, and also the equation that's looking at the voltage across the inductor. So that's LFF times di by dt, right? And where I is basically your field current. And so this equation represents your voltage across the field circuit. Now, when we have the motor or the machine operating in motor mode, then obviously you have basically the source, so that's E naught, and then you'll have your resistor in series with the source, and then you'll have your terminal voltage. So we write that equation in terms of the terminal voltage VTA. And now if it's in motor mode, so the current will go from the terminal into the machine. So then the terminal voltage will be the sum of that source voltage, then the drop across the armature resistance, and that's your basically representing the armature MMF, right? So L di by dt. So that's the armature coil that's being represented there. And so if you look at your transient equation in the what we derived in the what's called the generalized machine theory, you remember we derived this equation. So this is appearing here again. So it's giving you the terminal voltage of a DC motor in equation 7. Now, again, we've shown that EA can be replaced by this part using equation 5. So Kf times IF omega m plus these two terms. That's equation 8. And when we look at the output torque, so your output torque, which is TE, which is given by KFIFIA, that will be equal to now the J times P omega, so that's D omega dt, right? And that's TL. So TL is your load torque and J is your moment of inertia of the motor. In the generator mode, remember now a current is coming out of the equivalent circuit. So now you will have your induced voltage, and then you'll have to minus those two terms. So that's minus IARA and minus LAQP. So that's di by dt. And so again, this term we've derived it when we were doing the generalized machine theory for a DC generator. And so again, you can replace the same concept. We replace EA by this part here, equation 5, and you can write the total applied torque to the shaft of the generator being equal to J d omega m by dt plus TE, which is your electrical torque of the generator. So that's your generated electrical torque. So if you're applying mechanical torque, so that will be your Tm here. So Tm is equal to Jd omega by dt plus Te, where Te is your electrical torque, and you can write it as Kfia. Right, so those two equations now, so equation, that's equation 8 and equation 12, sorry, equation 11, they will represent your equation for the terminal voltage of the machine, right? Now, in the next section, we will look at, as I said, the transfer functions of those machines. So first, we'll look at the DC generator transfer function. So we start with the field circuit. So that's equation 13. So VF is, as I said, RFIF times L DIF by dt. And we can basically factorize the resistance of the field circuit outside the equation, and that will be turned out to be 1 plus TF times P, where IF is taken out of the equation there. So P is di by dt, sorry, d by dt of this particular variable. And when you take out RFs, and so you get this time constant TF here, which is basically the ratio of the time constant of the field circuit, which is LFF over RF, right? So this is showing you the magnetizing characteristic of the generator. So EA naught versus IF, the field current, and this is showing you the saturation curve, and this is showing you the air gap line. So for constant speed, so being that omega m is equal to omega naught is constant, so you end up with the induced voltage EA naught being equal, being proportional to the field current. Okay, so you'll have a constant times the field current, where Kg is the slope of the air gap line at constant speed omega m naught. Right, so equation 13 that we've written here can be rearranged, as you can see here. I'm sorry that it's not very well, the subscripts are not very well shown, but I will just confirm those variables with you guys. So so dIF by dt, right? So this is IF here, is equal to 1 over tau F, right? So that's F, and that's VF over RF minus IF. So that's the, we basically made, if we go back to this equation here, we've made PIF the subjective formula, right? So we've sent a PIF on this side, and we've basically written the equation 15, right? So this is the whole transfer function of the generator. So we have, using this equation here, we've basically used VF over RF as the input. And as you can see there, we minusing IF, right? So that's minus IF in block diagram form. And so basically VF over RF minus IF, so you multiply by this gain here, which is 1 over tau F from this equation above. And that, if you integrate that, you basically end up with the current IF, right? So here we have basically IF, the field current, and this field current now, if you look at this equation 14 here, if you multiply by a constant Kg, you end up with the induced voltage EA naught, right? And that's minus basically, sorry, the product of EA naught times omega m over omega naught will give you EA, which is the output voltage of the generator. Okay, so the generator output voltage is given by equation 16. Now, if we write this equation, which is EA naught in Laplace transform format, so EA naught S over VFS, so that will give you basically kg divided by VF times IF, right? So we're basically working in this part here, and you can write VF using the transfer function that, sorry, the equation that we've used. So VF can be written as RF into 1 plus tau Fs brackets and times IF. And you end up with this part, right? So this is the relationship between VFS to EA naught S, right? So you get this transfer function, which is kg of RF in the numerator, and the denominator is 1 plus tau F times S. Okay, so this is the first transfer function that we end up with the DC generator. Now we look at the second one, which is the separately excited DC motor transfer function. Right, so as you can see, we've already written this equation before. So that's the equation Vs, which is your supply voltage to the motor, right? So we're looking, this is Vs, right? And this is separately excited, meaning that you're generating your field current separately from this source. And the current IF will generate the flux onto the motor. So here Vs is equal to EA plus RA times IA plus LAQ times PIA, right? Where P is dR over dt. So your EA, the induced voltage, is proportional to the speed of the motor. So EA will be Km times omega m. And the torque balance equation, so your total torque will be equal to the load torque plus J times P omega m. And that will give you equation 20 there, right? And so this total torque is given by, remember the equation, we had Km times Ia, and the load torque is given by the product of B times omega m. Right. So if you write equation 18 in Laplace form, right? So we apply the Laplace transform here. So Vs will become Vss, that's EAS, and this LAQPIA, that's this term here. So Laplace transform, it turns into LAQ, which is the constant part, and that's S times IAS, right? And here it will just be RA times IAS, right? So that's your Laplace transform applied to equation 18, and equation 19, you apply Laplace transform. So the speed of the motor is omega m, right? Omega ms, and that's your constant, and that's your voltage, induced voltage in the motor. So that's EAS. And lastly, we apply the Laplace transform to equation 20, and you end up with TS TLS plus J times S omega m. Right. So this is your the three equations basically describing the DC motor in Laplace transform, or which is in your S domain. So we can now manipulate the equation to end up with the appropriate transfer function. So first, in equation 24, we are making IS basically the subject of formula here. So that you end up with Vs minus Ea over RAS LAQ. And you can factorize RA outside, where now that generates two constants, as you can see there. So factorizing RA outside, you get the ratio of tau A, sorry, being LAQ over RA. So that's your armature circuit time constant here. And the second factorization is basically generating tau M, right? So that will basically appear in this part here. So that's in equation 25. So on top here, I've basically replaced Vs using equation 22 and rearranged it there. So you find that Ia is equal to Km over Ra times those terms here, right? Where tau A is explained there in the at the equation below. And the product of Km IAS over J is equal to Ts over J, and you can rearrange that also and manipulate it. So that's where we now describing tau M as Raj over Km squared. So that's called the inertial time constant of the motor, right? So this is the factor that we've basically replaced here by 1 over tau M, right? So 1 over tau M will be equal to Raj divided by Km squared. So this factor we've replaced by 1 over tau M. And this is the two time constants that are generated from these two equations here, right? So equation 26 is coming from the total torque of the machine, and this equation is relating to the total torque on the motor, and equation 27 is basically relating the total torque on the machine with respect to the speed. Okay, so if you look at the transfer function generated from this equation here, equation 27, so we're getting basically the transfer function of the speed to the armature terminal voltage. So that's omega m of Vs, and it's giving us the transfer function here in this equation 27 there. So 1 over Km tau M into tau A S plus 1, and that's the ratio of B over J there. And if you neglect the ratio B, so that's the mechanical damping. So if you neglect the ratio B over J to be equal to 0, it simplifies your transfer function into this equation 29 here. And you can basically rearrange equation 28 as shown here. And that's basically showing you that you can write the equation in the characteristic polynomial that you've encountered before, right? Which is the standard form of a second order system, right? Which is S squared is 2 delta omega ns plus omega n to the squared equal to 0, okay? Where omega n is your natural frequency of the system. So when we write it in that standard form, the transfer function shown in equation 30, we can basically write the equation for the natural frequency of the motor, and also the damping ratio delta. Okay, and just to confirm those variables here, so this is omega n equal to 1 over tau a, and this one is tau m here, right? And here it will be delta is 1 over tau a plus b over j, that's divided by 2 omega n here, right? So the roots of the equation 31, so the equation 31 here, the roots of this equation, so you have basically two roots, S1 and S2. So if your damping, then your natural damping is below 1, you will have your under damping case. If it's equal to 1, then S1 plus S2 will be equal to omega n. That will be the critical damping case. And if delta is higher than 1, you will have what we call over damping. And if delta is 0, so you will have no damping. So this is the normalized solution for second order linear differential equations, which you have studied in your math, engineering maths. So it's basically showing you the normalized solution that you basically get when you basically apply a step input to a second order system. So as you can see, when your damping ratio changes, right, you move from, for example, if it's higher than 1, you get what we call a first order response following a step input. Whereas if your damping ratio is below 1, so basically now you get that overshoot that happens. Now your system turns into a second order system where you have oscillations in the response. And the next two equations are just additional equations that are showing you that you can write the speed of the machine in transfer function in terms of the torque, the load torque on the machine. So it's showing you how the machine speed relates to the load torque, and it's giving you two forms. One is where the mechanical damping is neglected, so you end up with this transfer function, and that's if it's not basically neglected, that will be your transfer function for the ratio of the load torque with respect to the speed of the motor. Right. So the next part is your elementary motor speed control. So it's the closed loop speed control of a DC motor. Okay. So this is the structure of this closed loop speed control system. It basically from your output of your DC motor, which basically is generating your electrical torque here. That's your TL is your basically load torque, and omega m, the speed of your motor. So IF is your field current, and this block here is representing the motor transfer function, and this block here A is your gain of the amplifier in the feedback. Sorry, in the control system of the control system. So what it's doing, the system, is it's basically measuring the speed of the motor, right? And So omega m is being measured, and then it feeds back this speed to compare with a certain reference. So what is being done is the speed now, when you multiply it by the tacho basically constant kt, so that gives you a certain voltage et, and that's compared with the reference voltage. And so now the error signal from there is amplified with the gain of the control system, and then that's the transfer function of the motor. So in block diagram form, this is what we basically have in this system. So this is your motor transfer function, which we've used before, and this is the feedback part. So you can see the speed is fed back, right, with respect to the reference. Okay, so kt is the tacho generator constant. So the voltage et there, which is the terminal voltage of the system, is basically the product of kt times omega m. All right, so that's equation 37. And basically the supplied voltage, that's basically the voltage that you're applying to the motor, Vs, is basically the product. So basically that's the voltage that will appear here in this part here, and that's basically the product of K, basically Ka times the error that's appearing here, right? So now Ka is basically the combined gain of the error signal amplifier. So basically this block here, and the ratio of ER over KT is the steady state no load speed setting, right? So this constant K naught here, as you can see, is comprised of three parameters. One is the tacho constant, one is Ka, which is the combined gain of the error signal amplifier, and then you have Km, which is coming from your motor constant. So you will see that this gain K naught will enable you to control the speed of the motor, because it links to KT you can't change. So this one is a constant of the tacho generator. Ka is the factor that you can increase or decrease, and that will allow you to basically determine what kind of response you have on your speed control system. And Km is basically coming from your motor, so you can't adjust that one. So our only change that we will basically have control on is Ka when we are designing this speed control system. So now let's investigate the mechanical speed response to changes in the reference voltage, right, and the load torque. So this block diagram here, you can write the equation. So delta omega m over ER is given by this equation here. And when we simplify it, we end up with this transfer function here. So so that's basically relating omega m versus the load torque on the motor, right? So from equation 41, we can write the undamped natural frequency of this system. So that's omega n, and that's and also the damping ratio, which is delta here, right? So equation 42 and 43 is describing the natural undamped frequency and the damping ratio. So how basically we get the final steady state response of the system. So we take basically the final value theorem that we're going to use in this basically expression. So what we are doing is we're saying as t tends to infinity, right? So in the time domain, as t tends to infinity, basically achieving steady state, and basically in the final value theorem in the S domain, basically now that becomes the limit SFS where S tends to 0. Okay, so this is the function that we can apply when we solve this equation here. Basically, in the S domain for basically solving and determining the final steady state response of the speed to a, for example, step change in the load torque, or a step change in the reference voltage on the speed control system. So it's giving you both equations here, equation 44 and 45. So you end up with this solution. So that's minus RA over Km squared, 1 over 1 plus K naught. So we will basically look at those cases in the tutorial so that you can get familiar with how this particular model is used to determine the steady state response of the control system. So there is a worked example here. I will go through it on Monday with you together with the tutorial. So for the weekend, kindly try and attempt the tutorial questions, and also go through this example. The solution is already provided in this in your set of notes. So this is basically the last section that we're going to cover in this course. And after that, basically we will have, basically, as I said, most of your assessments done from now on. So Monday we will have basically a tutorial session on Monday on this last section, and we'll go through the tutorial questions and discuss anything that you may have, or anything that you don't understand. You can ask me question during the tutorial. Okay, so we'll meet on Monday at 12:20, and we'll go through the worked example and the tutorial. Thank you, guys. We'll stop here for